Sorry, we were a little late today. So I'm going to open up the floor to questions. So today's going to be a review again. So everybody's on the same page. Remember, we are for the exam. Basically everything's fair game up until Diels alter, cope rearrangements, and what you're not responsible from that is going to be diastereoselectivity. selectivity. So I expect you guys to be able to know the molecular orbital, be able to identify HOMO and LUMOs of alkenes, dienes, trienes, understand why the Diels-Alder will react. I also expect you guys to understand thermodynamics and kinetics to a certain extent, at least able to make a rational argument. What do these terms mean? Why would you need them? You'll also want to know every reaction that we've learned to date, right? Expect to get questions that are asking you guys what's the product of a given reaction, or ask you what the reagents would be needed to carry out a specific reaction. And obviously we'll need synthesis as well, and then there could be other questions likewise. But I feel like if you guys know the reactions, you know the mechanisms, right? I think that's one of the things that can take some time. Know the mechanisms. Sometimes you guys can figure out these mechanisms on your own. And again, there's a good chance there will be a mechanism on the exam or on the exam that will be fairly difficult, right? That will require you guys to think. It's not necessarily going to be one that you've seen before, right? But the important point is that you don't throw out all the sort of basics when you go through these mechanisms. You make sure that you're not, what you're drawing in terms of those arrows are the products, and you're actually working through it rationally. So anyways, I'm going to try to get the room downstairs for Monday as well, so we'll have the 2 rooms. I'll email you guys, or at the very least I'll probably, at a certain point, take the first group of people here and send them downstairs or something. It's more comfortable down there anyway. So I'll let you guys know, and I'll post things. But questions? Is there anything else you guys would like me to go over in particular? Yeah. For Diels-Alder and for Cope/Claisen. So you are responsible for organic 1 material in principle, right? I think last year it was a little bit different. You guys had carbonyl chemistry. So, if, for example, you are doing a synthesis problem and you try to brominate an alkene, right, I expect you guys to recognize that that's a stereoselective process and draw the right stereoisomer. Otherwise, might lose points, right? So yes, stereochemistry is going to be important, but Diels-Alder and Cope, those can be a little bit more challenging to see and to work through. But yeah, all the previous stereochemical reactions, for sure. No. So yeah, I guess when I say, yeah, I mean, NMR, it's obviously really important, but I think that the majority of things that we're learning this semester, I guess when I'm saying organic 1 material, what I really mean is organic chemistry 1 material that builds upon what we learn, right? So if I say, for example, throw down a question where I have a chair conformation, right? If I trying to think, like I would expect you guys to be able to draw chairs if need be, or at least recognize the chair. I'm not going to ask you a chair conformation question, but it's possible that I could throw a chair into a structure, or it's possible that I'm not saying that I will, but I'm allowing myself the option to do things like throw a question there with a chair, throw a question, probably not a Newman projection, but maybe you guys should be able to do Newman projections. But yeah, no spectroscopy. Yeah. Yeah, I mean that's Cope and Claisen. So what you're talking about is, yeah, so Yeah, so those are sort of sigmatropic rearrangements. You mean pericyclic, like?
Yeah, the differential reaction is repeat, and we can have a problem with that.
So yeah, I mean, from that standpoint, again, like I said yesterday, like it's a lot of the same stuff from like the quiz, right? So like if I give you a diene and ask you sort of what the product of that reaction would be, right, thermally, I would expect you guys to be able to tell me. So this is sort of very superficial Diels-Alder chemistry, right? So I expect you to be able to, right? So I would expect you guys to be able to tell me that reaction. What I'm not going to do is, like I said, I'm not going to suddenly throw a couple groups on there where now you have stereocenters that you'd have to know. So that's what I'm saying, like, yeah. Absolutely, yeah. So yeah, and why? Yeah, so right, so the question was conjugated dienes. Can Diels-Alders take place with, say, for example, sort of a skip diene, right? And again, these aren't, this and this are not part of the same system, right? They don't have the pi orbital overlap. And you need that, right? Because of the sort of how the sort of molecular orbitals look. Yeah.
So what else on chapter 20 do we need to know?
So thermodynamics. You guys asked me the chapters. I got to be honest. I don't know. What's chapter 20? Right? Is that Diels-Alder?
Yeah.
So I expect you guys to know Diels-Alder, Cope-Claisen. Is thermodynamics of dienes on that one? So I expect you to know that. Yeah, I mean, like that's what I'm saying. Very superficial. So much in the same way like the quiz. Like I want you guys to know what a Diels-Alder is, but I don't expect you to know the more complicated aspects of it. With the exception, because again, I recognize that stereochemistry, especially Diels-Alder, Cope, that's going to take a lot of practice to get down, right? And we have a lot of other materials. So that's going to be saved for the next exam, where we'll probably put a bigger emphasis on those things. Really, the focus of this exam is going to be largely reactions, mechanisms, synthesis. That's probably going to comprise 80 to 90% of the exam. So if you know all the mechanisms, you know all the reactions, and you're good at synthesis, you should feel pretty good. When averages are 60, right, 50 to 60, what does extra credit really do, right? No, I mean, I'm like serious. It's like, so whatever. It's out of 110 instead of it doesn't really matter. They're still the same breakdown. That's maybe the way that I came out meant different than what I meant, but my point is that it's not like this is a 90 and above is an A and 80 and above is a B, right? So the extra credit would simply be, now the exam's out of 105 rather than 100, and that's kind of doesn't really do anything. So, I mean, I could throw up questions, but so if you guys have a specific thing that you'd like me to throw up, if you want me to throw up a mechanism question, if you want me to throw up a synthesis question. Synthesis, so I guess we'll do both. So I'll start with the mechanism, I guess. That would seem like the order, the sort of order that would make sense, right? All right, so let's see here. All right, so when I was in grad school, see if I can get this right. Very close to putting this as an exam question on the exam. I'm not going to get the structure right, but whatever, I'll try my best. Actually, maybe I can get it right. I think I can get it right. Let's see here. All right, I actually don't remember this that much, but I'll just try to make something up that serves the same point. So, um, okay, this is whatever. Just ignore everything over here because that's not really that important. So let's say you take this molecule here. It's actually almost became a research area of ours. And there's a cladocorin A or something like that is the name of the natural product, but basically what they think it is it's a product that arises from this other anti-cancer molecule that people are working with. It has this molecule, well, you have here called gamma hydroxybutenoide. And what the product was that formed was kind of neat, I thought, kind of this neat bicyclic system. Screw up drawing it and try to get it nuts. Okay, so let me see here. This is a little bit complicated to see. We'll just make this an H here. The steric chemistry doesn't really matter, but here's a sort of a mechanism question for you. It's a little bit more on the complicated side. It's actually not super complicated though. If you sort of break it down and think about what we've learned here. And again, there's stereochemistry associated with this. Let me just take a look at it, make sure I didn't screw anything up.
That thing next to the O on the left, that's what you connected with the line there.
So this is going behind this oxygen right there. So this oxygen is coming behind. So let me maybe use a color to. So let's pretend like this one's going back. And this one's coming sort of towards you guys. Okay. And then we'll pretend that this one's coming here. And again, this is something that in the literature, there's a natural product. The name of the natural product was, but it sort of had something over here that looked like this. And there's another component over here that had something that looked like that. And again, this is actually a mechanism. I contemplated putting this on the exam, but then I thought of something else. In part because I thought that it built upon both carbonyl condensation chemistry as well as certain things that we learned about Michael additions and so forth. So, start working through it. Want to see pen to paper. But as you're doing it, I think what you should recognize, right, is just see where the bonds are forming, see where the bonds are breaking, and from a sort of a retro synthetic standpoint, right, what you may want to sort of think about is, well, what if I broke the stack the other way? Sometimes you can start thinking in reverse as well. Just by chance, does anybody think they see it? See a few hands, I see. So just think about what we learned. Again, this is completely out of left field. It might look like it's out of left field.
Is that an OH at the top? Or is that?
This is an OH, yeah. So this is an OH. Okay. A little bit of acid. Again, this was actually an interesting, because I think I had this in my thesis. It was a while ago that I thought, I think it's cladocorin B or something like that. But again, it's sort of leufolide is the name of the natural product, I think, that led to, I think, this molecule cladocorin A or B. And again, what they saw was this molecule that had this interesting structure to it, but then somebody thought, oh, well, maybe it's just an isolation issue. And there was this known natural product, and they thought that just through the acidic conditions of the isolation, that it rearranged to generate a molecule that looks something like that. And again, it's not probably perfect. It's sort of general. So what do you notice? Like, I think if you're struggling to see exactly what's happening here, what are some of the things that might stand out structurally in the problem that might at least lead you in the right direction? What are some things that we've seen this semester? Yeah. So you see what? Attacking the carbonyl. Okay, well, why doesn't everybody start there? Have this attack that carbonyl and see what product that would form. Does that make sense? Is that something we've seen this semester? What's that? If we protonate carbonyl, can we protonate the carbonyl? Yeah, why? Because we're under acidic conditions. So yeah, start there. So everybody protonate the carbonyl, and then just have this do a intermolecular addition. So everybody else can try and draw that. And again, this is, why did you think of that? What's your name? Linda, what made you think that? Yeah, she noticed this component. So a lot of it's just sort of dissecting the problem. Again, I can't teach this, right? This is one of the reasons that you guys have to learn a lot of this and work through these problems yourselves. But Linda noticed that this oxygen, which she thought was this oxygen here, had to make a bond with this carbon, which was this carbon here. And she figured she could do that, right, because there's a carbonyl, and we've seen reactions, right, where alcohols have, for example, condensed with carbonyls, right? That's one of the big carbonyl chemistry reactions, right? Condensations of carbonyls and alcohols to make ketones, right? Then the question is, once you see that, there's something else that's going to happen. So everybody try to work through that. Again, everybody protonate this. All right, I'm sure everybody at this point can protonate that alcohol. And adding to that molecule there. Yeah, actually, this is definitely not the natural product. This is, I think, closer to what one of these we try in lab. It should work out. And maybe I'll explain why in a moment, why this actually wouldn't work. So I think I just had the wrong disconnection. But whatever. But this is not. This is close to the method. This is the general same kind of idea, but it's not that. So again, this is going to be protonated still. Right? Okay, what's the next bond that we need to make? This oxygen here is bonded to where? Right? So this guy is this guy here, right? You can sort of see that in there. You see how that double bond? Now, what type of reaction would we want to do that, right? Like if we're going to do this, make this bond, how do you think we would facilitate that? What type of molecule is this? It's alpha-beta unsaturated. So we've seen this molecule specifically in Michael addition, we saw in cuprate additions. Those are the two areas where we saw this, right? And what needs to happen is a nucleophile needs to attack here. Given the fact that we're under acidic conditions, what do you think might need to happen first? Yeah, we're probably going to want to activate this, right, and make it a better electrophile. So what we'll do is a proton transfer. Okay, so since we got this proton here, again, so proton transfers are just proton transfers, right? You can just do it intermolecularly if you want. Certainly, in principle, it's almost likely the solvent coming and grabbing it. But this is one of the things I will allow you guys to do, is to simply say proton transfer. You know, it's not going to happen. Well, sometimes it can. But the chance of this reaching all the way up there to grab that is going to be too high strain. So yes, probably something else grabbing it, reprotonating it. But proton transfers are going to be happening a lot. And so to save your guys time and so you don't get carpal tunnel drawing it all the time, I'll just let you do this. okay? And now that we've activated that carbonyl, now this hemiacetal can condense. All right? Everybody see that? So again, this is what we would classify. So sometimes we'll see mechanisms. You know, have we seen oxygen add 1,4 into alpha beta unsaturated esters before? I have. You guys? Probably not. Maybe you have, but probably not, right? But this is sometimes when the mechanisms come up. You say, all right, I've seen oxygen behave as a nucleophile, right? I've seen this component be an electrophile, and so this is sometimes how you kind of ask these types of questions for mechanisms. It's not something that you've seen before, but you can at least rationalize it because you've seen oxygen behave as nucleophiles before. You've seen alpha beta unsaturated carbonyls exist as electrophiles, and I won't ask you to figure this question out. Like, you know, if I said predict the product of this, I'm not going to ask you to predict this product, but certainly in a mechanism problem. This is one of the things I like to sometimes do is have you guys rationalize this type of scenario, right? And now we'll have right? And so we'll get to something like that, and then what's the last thing that's going to happen? Sorry, I have a proton. What's that? Yeah, so we're going to deprotonate, and then we'll get the keto-enol tautomer, right? So this is an enol. It'll just go to the keto tautomer form. So you guys yeah. Do it. You're allowed to use pencil. Okay. I photocopy all the exams. So yeah, so we photocopy them. So certainly it's fine to use pencil. So anyway, so this is sort of a more complicated. Now this I actually tried something very similar to this in our lab, and it didn't work out in part because this was not the Nalthorpe product. I think that this was actually attached here. And that makes a big difference, in part because of this intermediate here. What do you guys see about that structure there? This is just sort of a side note. What size of a ring is that? 1, 2, 3, 4, 5, 6. And what do you notice in that? There's this trans double bond and a 6-numbered ring. Probably not going to work. In fact, the one that we were making, I think, was a little bit further extended, but it's still the same issue. So anyway, so again, this is a more complicated mechanism problem. Again, this is a type that I'm not going to make your whole exam like this, but you may get an exam like this, or you may get a question like this, and I certainly think it's well worth to prepare, especially when you're practicing. Now, if you're not comfortable with mechanisms at all, I think it'd be a waste of your time doing problems like this because you're really not going to get anything out of it. But if you're getting really good at mechanism problems, you feel really comfortable with mechanism problems, I think it's then worth it to sort of step into those next level questions. So I'm not suggesting everybody try those harder mechanism questions, but I'm suggesting for those of you that feel more comfortable and confident with mechanisms that you can start some of these. And even those of you that might not be, you can try it, but again, just take it one step at a time. It doesn't necessarily mean that you have to get to the final product per se, but you want to sort of, as you're working through it, really ask yourself, does this step make sense? You know, am I drawing my arrows right? Because that's one of the things I often find is that students, it will completely fall apart. I'm going to get to the synthesis problem, but you had a question related to this?
Do we know all the mechanisms for the reagent?
So should we know all the mechanisms? Oh yeah. Yeah, I mean, well, I think that you should be able to. So my general rule is until we get to transition metal catalyst chemistry, you are not responsible for mechanisms involving transition metals or transition metal-like reactions. And what I mean by that is, for example, hypervalent iodide, osmium tetroxide oxidation. I don't know that we've really seen anything like that. But things that simply involve acid-base, Bronsted acid, Bronsted base, nucleophilic, electrophilic, elimination type mechanisms, I expect you guys to know all of them. And in principle, and I've said this to people, you know, I hope that you guys, one of the things that I hope that you guys, one of the things that I hope that you guys get to the point that you can do, and I know it's not necessarily realistic that all of you guys do this, but I certainly push you to really do it, and I hope to get you guys to be able to do this, is to see a new mechanism, or to see a new reaction that you've never seen before, and be able to reason it, right? And be able to reason a mechanism through it. I think that's often the best place to be if you can get to that point. That's why I put such an emphasis on mechanisms, is because oftentimes you guys can rationalize new reactions simply by knowing all these different ones. So yes, I want you to know them all, but what I hope that you get to the point where is you don't have them memorized, right? I don't want mechanisms to be memorized. I think that's can be very difficult. I want you to be able to reason through them. And so going through all of the mechanisms and being able to go through the mechanisms, every reaction will be, I think, very helpful for you on this exam. So let's just say that. Furthermore, we're going to do some synthesis problems, and I often think that sometimes even within a synthesis problem, you can think about mechanisms. I think it's worth it to, even within a synthesis problem, think about mechanisms. Because, you know, one of the big issues that I think transcends both mechanism problems and synthesis problems is students draw structures that completely disobey the rules of like basic foundational chemistry, right? Like you'll run a reaction and suddenly you'll just lose a carbon somewhere, right? And you don't necessarily mean to, it's just a drawing mistake, right? Or you'll you know, just completely lose a charge in a molecule, right? So you'll do these things that will sort of disobey the idea of conservation of mass, conservation of charge. And this is one of the things that I hope that you guys push through in mechanisms. But you'll see the same thing come up because it transcends even mechanisms and even goes to synthesis problems, right? And if you think about the mechanism, if you get really good at mechanisms and you start thinking about that, that sometimes you can reason, okay, well, I'm just making these bonds here, and you won't begin to make, I think, what are fairly common mistakes, which are often kind of almost typographical in, you know, in nature. All right. The synthesis problem. One of the things I've noticed when people have come to my office, I'm trying to think of the last time we discussed synthesis problems a little bit, is that you guys seem to completely ignore retrosynthetic analysis. And I think we brought this up last time, so maybe it's worth me putting a synthesis problem that will sort of force retrosynthetic analysis. And also at the same time refresh reactions. Linda?
Yeah.
Draw a molecule that has 8 carbons on it, and then just pass it off to Neeson, and then you're going to put a couple oxygens on it. So go ahead and draw it, and we're going to throw it up on the board. It's like a magic trick. I need a volunteer. Yeah, so this is just because I will see. Again, I have no idea whether we'll get through it, but at least the strategy will be clear. Just draw something with 7 carbons. Eight. And then throw a hydroxyl somewhere on it. Throw a couple. And then give me the paper. And what we're going to do is we're going to see if we can synthesize this molecule. I really feel like All right. Not too bad. All right, so we'll see how this turns out. So what I want to do is I want to break this molecule down. So here's the structure. Strap. So we've got this molecule on here, and from a retrosynthetic analysis standpoint, let's say, can we break this down to 2 carbons or less? So we want to break this entire molecule down into sort of pieces of 2 at a time. Okay? Now, from a retrosynthetic analysis standpoint, what you'll often want to do is sort of look at the molecule, and absent from, sometimes you can have that 2 carbon in the back of your mind, sort of be like, oh yeah, that would be good. But you're often really not worrying about that. You're just sort of thinking about what could be the precursor to this molecule that would be a single step to make, right? And so one of the things that we'll do is 2C or less. So from 2 carbons or less. And when we look at this molecule, we start to ask ourselves, what can we make this from? Right? What could be the possible, just one step? It can be whatever. Like, oftentimes I'll be in my office explaining to somebody retrosynthetic analysis and be like, oh, we can do that? It's like, yeah, this is just a strategy to build a molecule. There's sort of a freedom to retrosynthetic analysis. What might be a bond disconnection that we could use that could sort of make this? I mean, what are our functional groups? Yeah.
That there was an alcohol that there was a 2 carbon at the top of the back and the lower support.
Yeah, hold on, let's just one second. Right? So does everybody notice this by chance? Right? So this is an alcohol disconnection, right? So this would be one possibility, which is actually a kind of nice one, right? And again, it's an aldol disconnection where we take this molecule here, right, and we treat it with some base, right, potassium cubietoxide, for example, and benzaldehyde. So this is kind of a nice one, right? Like, followed by what? Dilute acid. Oh, sorry, not benzaldehyde. My mind's somewhere else. Acetaldehyde. So yeah, so acetaldehyde. Sorry, that what I had would have had a phenyl group there. So it's methyl. Okay, so this would be one possibility. It's actually a nice possibility, right? When you see this one, it might be you might like this right away. Why? Might this be one that would be useful for this type of question? Yeah, it's a carbon-carbon bond forming process, right? So that's good. It's gotten rid of 2 carbons, and we know that it needs to be 2 carbons or less. So it's kind of a nice potential starting point. Doesn't necessarily mean you have to keep going from here, but this seems like it's probably a good place to start. Where else could we start? Yeah. Dilute acid. So what would happen if I simply treated this with cubietoxide, and that would just simply be the aldol, right? So you need to dehydrate afterwards, and so that's usually there's some acid, dilute acid. So I just put acetic acid or something. So you just treat some acid to eliminate. Usually it's like dilute HCl. Yeah. So it's just some acid that's going to promote the dehydration process. Again, on an exam, like to be honest, on the synthesis problem, I'm a little bit more free to these things. I don't really worry about this too much. It'd be more in a sort of a reaction question. So if you like want to do an aldol condensation and you're like with benzaldehyde, you can even just write aldol condensation. But I'll know what you mean as long as it's right? So, but what else? I like this one, and we'll probably end up going with this one. But just from a retrosynthetic standpoint, is there anything else that we might be able to do? How else might we make this molecule? A Wittig, right? So a Wittig would make the same carbon-carbon bond, right? From the Wittig standpoint, we've got 2 possibilities, right? Because the Wittig, we could have the triphenylphosphine on this side and the carbonyl on this side, or we could reverse it, right? So we could have Well, there's not really sister trans here. You're gonna, in both these cases, honestly, you're not gonna get selectivity. We haven't really learned chemistry. So here's one possibility, but, well, we'll get to that. I'm gonna write up the other one and then you can bring up that concern because that's where I was going with this. Right? And as was just brought up, right, the issue with this one up here might be that it might react with any one of these carbonyls, and so selectivity might be an issue there. So again, this one's still sticking out as the best, but this is another option, right? And that's what we would ask for. How else do we do this? This one would probably be a little bit better. Then we would have to make this. How do you guys make Wittigs? Yeah, no, I think I heard the right answer in many different ways. Right? You treat triphenyl phos, but you have to make it, you have to deprotonate it from the triphenyl phosphonium salt. So some base, potassium cubic-oxide is fine. Right? Butyllithium is fine. Some base, right? And then how do we make this? Yeah, so the bromine would be the leaving group. So we treat triphenyl phosphine. From that, right? And triphenyl phosphine. So that's so you guys know, right? But again, even in this case, now we're saying, wow, I still am using the same thing here, right? And this really isn't any more simple. In fact, it's more complicated than what I had over here. So again, you sort of look backwards and then you evaluate. I don't think we're going to beat this disconnection, but it's a good thought process anyway. So again, so we sort of evaluate alternatives. This is retrosynthesis. Again, the idea is that you can go through retrosynthesis with this amount of rigor when you're practicing. Obviously, on an exam when there's not necessarily as much time, hopefully you'll sort of be a little bit more, you'll sort of be a little bit quicker seeing some of these things. But you got to sort of practice it, and certainly at the beginning to get comfortable with retrosynthesis can be useful. So there was a Wittig approach. All right, so we're focused on this alkene, right? Are there any other ways that we might be able to do that? Imagine elimination. Again, we can keep going down this alkene, elimination, everything else. I don't think we're beating this. What about perhaps another disconnection? Right, or even a functional group modification. Maybe what if one of these was an alcohol? So right, so there would be another option, right? So basically get the anion there and treat it with this. So this would be an option. But what might be the problem with this approach? I mean, from a practical standpoint, this might just start polymerizing on itself, right? This might react with itself. Right? You can somehow perhaps get away from that by just having a ton of this so that it sees more of that, so you could do that, but that would be from a practical standpoint. Again, I'm not too concerned about this. But I think from a basic disconnection standpoint, that's fine. But again, it doesn't seem to be as good. I'm gonna make one more, but again, to sort of prove this point that there's literally infinite number of ways in which you can think about this, and someone just happened to identify right off the bat, I think, one of the best ways. But certainly another way that we could do this would be even, so you guys have been focused on carbon-carbon bond forming reactions. I think that's good, right? Those are some of the most valuable ones, especially if we're trying to break this down. But sometimes the carbon-carbon bond isn't necessarily the best place to start, right? Sometimes it can simplify things if we begin to think about, say, for example, something like that. Right? So let's say we can do an oxidation, right? We know that we can make ketones from an oxidation. Again, we don't have to worry about both of them because we're saying that we're going to make this, right? And so we can imagine scenarios, right, where perhaps this could be a disconnection, and maybe then we could do, say, for example, an intermolecular Grignard or sexual reaction known as a Thales-Hillman, but that's more advanced, not for this class. But there's other disconnections that one might imagine from this molecule here. Okay? Now, that's an important point, though, because I think that's something that you guys, it's worth at least considering. And there was actually a problem that was similar to this on the worksheet. It was this here, right? It was on one of my worksheets. So the question was, here's a molecule, right? How would I make that from sort of 3 carbons or less? Kind of same type of question here, except I said 3 carbons or less at this point. And I think that without, this is one of these instances where, you know, how might we do this? Well, again, you might recognize, say, for example, a Grignard here. Right? Like that might be something you might do, but what would be the problem with this? Yeah, so the Grignard, again, if you have like the same problem with alcohols you have with amines, right? This is gonna deprotonate this readily. So then you have to protect that amine, which we really haven't learned about amine protecting groups yet. We'll learn about those when we talk about peptides, right? You guys haven't learned any amine protecting groups at this point. Yeah, so we really wouldn't have anything to really use at that point. And so this is one of these scenarios where thinking about oxidation states might be helpful, right? Because, what's that? Well, yeah, that would be one option. That would be a Henry, right? So one of the things that was brought up was, well, if I have, hold on, right? And somebody said, well, hey, we were talking about these reactions called Henry reactions, which are very enolate-like, right? Which we discussed, where we can make this analog, right, of an enolate, right? So we can sort of react. So if you took something like this, you treat it with base, some base, right? You could do that reaction, right? So again, looking at a new oxidation state, what were you say?
What if you treat them with acid and water, so it would make the carbon?
If I treat the amine with acid and water. Are you trying to do like, I think you maybe think it's forward?
Yeah.
You're thinking of like the forward, I think you're thinking of like a pinnacle type rearrangement.
Yeah. Also, how do you reduce just one carbon on the other example?
You don't have to. It's I'm not reducing,
Okay, fine.
right? So I can do whatever I want in the reverse direction because I'm moving this way. So yeah, there's no selectivity issues that we have to worry about. We'll worry about those down here, right? Because, you know, I'm just oxidizing. Now, if I had a OH here, and I'm saying that somehow that's going to come from 2 OHs, and I'm going to somehow oxidize one selectively, that's when I worry about that. But in this case, I can oxidize, and it's not going to matter because this one's already at the full oxidation state. But somebody brought up the other option that I was thinking. So this is one oxidation state of a nitrogen, right? But you could perhaps look at the cyano, right?
How does the NO2 become NO2?
Oh yeah, nickel. So, sorry, nickel. You can reduce nitros. So it's the same. It's analogous to like, somewhat analogous to carboxylic acid in a way, or yeah, nitros can reduce. But again, the cyano, same thing, right? You can reduce cyanos, basically same type of conditions, right? LEH. Again, in thinking this way, it might not help you, but sometimes it simplifies it dramatically, right? So we look at this, and now can we see a nice way to do this? The answer is yes, because we've seen one of the first one of the nucleophiles that we often see right at the very beginning, because they're great nucleophiles, are cyano groups, right? So in this case, what you have is lithium cyanide or something, and then do that workup, right? So again, I just wanted to sort of make this point, is that it's always good to kind of consider carbon-carbon bonds. In this case, I think it works out really nicely because you quickly identified, I think, a nice disconnection, and if those work out well for you, that's good. But if you can't apparently see that carbon-carbon bond, which I think is the case here, then maybe what you need to do is consider alternative oxidation states. Yeah?
I know that enolate work in acid also, but does Henry actually work in acid?
I don't know. Good question. I'm not sure.
What about non-acid and non-acid?
I mean, we haven't even really been discussing aldol chemistry and acid, right? Like,
But it's acid.
yeah.
I raised it up. The other question was how big was that?
Yeah, it was an oxy-Michael, but I think do you think that you're going to be tempted to? You're not, because you're going to remember this conversation. Yeah, I mean, honestly, I think for the most part, this is sort of keep things. We really haven't discussed, like, really, I try to avoid teaching you guys the same example of the same type of reaction over and over again. It's like one of the reasons why I didn't teach you guys Horner-Watson-Emmons olefinition, taught you Wittig, right? I think the same thing with like enol chemistry. It's like I showed you guys the enolate chemistry, protonated, right? So that's kind of going to be the go-to. If it's, say, for example, a mechanism question, it's good to know. If there's a mechanism question and it's under acidic conditions, and that would make sense to do that under acidic conditions, that's fine. But I would just focus on enolates, because that's, it's like enolates and isn't like the chapter called like enolates, enamines, or something like that? So like, just make the freaking enolate, right? Like, what's that?
First carbon, whereas you attack the second.
No, not really. It's the same thing. Mechanistically, right? It's the same thing.
Same mechanism, but they.
Well, no, but that's the point, right? Is that if you think about the mechanism, you're saying you're.
Where the next carbon.
No, because no. Well, it's the same thing, right? This cooler is like this. So just recognize that the nitro is equivalent to a carbonyl. And you don't have to think about, it's going to be from the one right next to the nitrogen. Like, because that's memorization, right? If you're having to be like, if I do a Henry, it'll be from the one adjacent to the nitrogen. No, just think about the Henry as being sort of a carbonyl surrogate, right? And you don't have to worry about those things. All right. Oh, I erased the freaking question. See what you did to me? Yeah, I'll remember it. Yeah.
So this question, what if you create an alkyl to protect the alcohol and you attack it with NH2 minus?
Oh, so you want to... Like an epoxide? NH2 minus?
That was what I'm saying. Like, let's say you make a haloalkane and protect the alcohol and protect it, and then
You want to do a, yeah, I mean, again, I don't know, probably. You want to somehow make that? Yeah. So, like, take the alkene, right, and that's not bad, right, because you could take that alkene and you could treat it with bromine water and get to that. You probably want to protect this, though,
yeah,
right? Yeah. But it's long, it's getting a little bit more steppy. But it's fine. Again, I'm not going to penalize you guys for having longer synthesis problems. But, it's just another reason why many synthesis problems have multiple, like literally an infinite number of different possible answers. All right, so what did we say? We said aldol. All right, so let's look at this guy now, right? So now that we have this one here, now we're going to look at this molecule here, right? And from a retrosynthetic standpoint, again, we can do the same sort of thought process. And again, if you want to start thinking about carbon-carbon bonds, you know, there's nothing wrong with going to that carbon-carbon bond. In fact, I would argue that if you see a good carbon-carbon bond disconnection, take it and run with it. But the point that I was trying to make before is don't limit yourself to just trying to make carbon-carbon bonds. Go with those first when you're thinking retrosynthetically, but then if you can't see anything too apparent or obvious, then you can start considering some of these other options. Okay, but in this case, do we see another, again, this is an enolate chapter, do you guys see any other potential enolate style condensation reactions? Or kind of just gave away the answer. Is there any other enolate style carbon-carbon bond forming reactions that we could do? Yeah. An internal Michael. Can we do an internal Michael? Well, let's think about that. Where would our enone be? Right? We'd have to add a carbon to there. That might be a little bit difficult to do simply because if that's, say, for example, where our Michael addition would add into, now that has to be our nucleophile. Right? That's going to be a little bit challenging, or vice versa. Right? And there is chemistry that can do that. It's called oolong chemistry, but what we've known, we really want to focus on where the really enolates are. So the better question would be if we sort of think about where those are, right? Here's an enolate, right? Is that really a good disconnection? Maybe, maybe not. Perhaps a better disconnection would be here or here, though. Right? One of these. Right? So is there any type of disconnection that we might be able to do that could lead directly to one of those? So we could do an aldol. The aldol would technically come from, well, yeah, so let me get back to the aldol. Sometimes when you're doing retrosynthesis, that's kind of what you just did, right? You thought 2 steps, and that's perfectly fine as well. Like, oftentimes when you're getting good at synthesis, you'll start seeing 2 steps, 3 steps ahead, and so that's kind of what we're seeing here, with sort of a 2-step. And I'll just draw one example. Right, but I think what was being thought was that, you know, it would be an aldol, right, because you can oxidize the aldol. And again, it could be the other way around as well. We could have the hydroxyl on one side, just do the reverse. But this would be one option. But somebody just brought up a Dieckmann, right? So this would be one option, would be an aldol. But the other one that might go directly to it would be the Dieckmann, right? What's the Dieckmann? Yeah, or the Claisen condensation. Exactly, right? So it's the same thing that we did here, and then we can look at one or the other, you know, but yeah, that would be the idea. We would either have, let's put ONE there for now, right? And we could do this one, or we could flip-flop them. Yeah?
I'm sorry, how does the top one get from?
So this is you're making this bond here. It's an aldol.
Also,
Yeah. Right. But yeah, in this case, it would just be sort of the LBJ, and again, this is same idea. Yeah.
So the synthesis problem, you have to write like you want a specific product, you have to write like
That's kind of what I was saying before, is aldol versus aldol condensation. I'm usually a little bit, I grade all the synthesis questions, and so I'm usually a little bit flexible, I think. Yeah. If it was a specific reaction problem, I might deduct, like say, for example, 4-point question, I might give you 3 out of 4 or something like that. I might deduct a point if you don't say dilute acid, or if you say dilute acid for an aldol condensation or something. So you know. So actually, I was using an example today. We were talking about ozonolysis, right? And somebody said O3 for ozonolysis, and I was like, yeah, in a synthesis problem, that's fine, just because you're kind of moving faster. In a reaction problem, though, on an ozonolysis question, I would expect you to put O3 and then DMS or some reductant, right? So just synthesis, I'm a little bit more, I'm more curious about you getting to the final product and that you know the reactions rather than the nitty-gritties. For the specific reaction questions, I'm a little bit more, I won't over-penalize you, but you might lose a point, just to for anything to reward the people that were more complete. Yeah.
What's the difference between the first one and the LBA and the second one?
They're just 2 different reactions. This is an enolate with this is an aldol, so it's an enolate reacting with a carbonyl, or so this is with a ketone or aldehyde. This is with an ester. The product in this one is an alpha beta unsaturated, is a 1,3 diketone. In this case, the product is a beta hydroxy ketone. Okay. All right. So I like this one, right? I think this one's pretty nice. Again, or we can go with this one. Either or. Yeah.
Wouldn't the top be more highly, or the top would prefer a more highly substituted alkyl?
Oh, you're saying you want to go the other way?
No, the top. Like it would move from there to the other, the top, right?
Yeah.
That reagent would react in exactly the way you want, right? Oh, no.
Yeah, no, I think what you're thinking is relative enolates. And I haven't actually defined anything. And this goes back to what I was saying before. Like, if we're trying to get an exclusive, more substituted enolate versus less substituted enolate, then that would be a question that would probably be more specific for that. And so that would be the type of thing where if I gave you a product of, say, for example, where you could get, for example, 2 possible regioisomers, you might want to say like 0.9 equivalents or 1.1 equivalents. Yeah.
You also have to use LDA, so whatever you put on the other side, you wouldn't be able to make that higher ring.
Right, so there would also be the reversible component to it. If you did deprotonate over here, that would be a much smaller ring to form, so that's another good point. So, but yeah, so it's kind of irrelevant for this type of, again, for a synthesis problem. It's not really relevant, but it sounds like, as was brought up, it probably wouldn't be a big deal. So again, we can pick either one of these at this point. Again, we don't care about the number of steps. This is a little bit shorter and more direct, but again, now we have to put that methyl group there. We're up here. We're all set. So at this point, I really don't know which one you want to sort of go with, but we've only got 15 minutes left, so let's just pick one. Hands for this one. Hands for this one. All right, so let's go with this one. And again, it might be easier. You might find that this one's easier, but whatever. All right, so now we got to sort of make this molecule here. Okay. At this step, we got a lot of, I think, wiggle room in terms of things that we could do. And I'm kind of curious to hear what you guys have to say, because nothing's screaming to me. Like the last 2 reactions, for me, allyl condensation was screaming to me, let's do that, as was the Dietzmann condensation. At this point, I don't really know, though. So let's hear some of the retrons. Yeah. Well, hold on. I think you're still confusing. You're still.
Yeah.
But it's kind of okay because a lot of reactions we can do go in both directions. So when you're saying saponification, this is a saponification. What we're really trying to do is go in the opposite direction.
No, then if you heat it.
But you're not going to heat. Well, you're trying to make this. You're confusing. This is why it's important to practice retrosynthesis because it is confusing. If you're constantly going in the 4 directions, sometimes it can be difficult to work in the reverse direction. So you're saying, oh, I can saponify this, but that's not the reaction we're trying to do. We're trying to think of what we can make this. But it's the same type of reaction, right? It would just be a transesterification, right? So it'd be like methanol and, say, for example, acid, right? And we might not be able to do saponification there, but maybe there is some other way that we can install CO2, or maybe some CO2 surrogate. So I like this, but let's just leave it out there for a second. Does anybody think of anything else?
Maybe longer, like, let's say, like, that started out as a update on unsaturated ketones, then you did that started out as an update on unsaturated ketones, that added that carboxylic ester with fermentation.
Yeah, I would be fine with that. It wouldn't work in principle. So you've basically done Umplong. So what you're saying is, and again, there's no reason to, I think it's fine. I would be perfectly fine with this. So I'll just put it up there. This probably wouldn't work in an actual lab. So Gilman 1,4, but we do have ways to do this type of bond disconnection. There's a reaction. Again, it's sort of oolong. What you do is you would take, again, we can talk about it later, but so, yeah, I think for this point that's fine. But it probably wouldn't work in principle. You'd probably use a different way. Yes?
Can you reverse the shift to get carboxylic acid on SOCl2?
Then?
Reverse the shift to get the carboxyl of that, and then do SOCl2 and then MgE to add a
Wait, hold on. The reverse?
Oh, wait, no, that'll be adding another extra carbon. Wait, I was saying the reverse of the shift to get a carboxylic acid, right?
Oh, from that? Wait.
Wait, aren't we doing from this to that?
Well, we're looking at both of them.
Oh, okay.
Yeah, I think for a synthesis problem, I wouldn't penalize for this, even though this, because I think based upon what you guys know, this is fine. And then again, this simplifies it really easily. I'm betting all of you guys could break this molecule down pretty easily, right? Yeah. No? All right, we'll stick that over here for now. I bet you guys could. It might take you a little bit of time, but I'm convinced that it'd be an aldol condensation, right? Right, and now you just got to figure out how to make acetone. But that's fine, right? I'm sure you could do that. How'd you make this ketone? So we're good here. How'd you make the ketone? Wait, say it again. Nesyl. Oh. Yeah. Acyl chloride. Perfect. Boom, you're done. Right? Good. I wasn't thinking that. That's perfect. Oh, sorry. Oh, so actually it didn't even matter. Oh, I'm missing it up here. Sorry. Yeah. Sorry. Yeah, thank you. Yes. Would this be sensitive to ethanol and methanol? What do you guys think? Maybe. Yeah, so the concern is, well, if I did this, maybe I would get the methyl ketal. How might we, if that was an issue though, how would we go around that? How might we go around that? Say, for example, we got here. We made this molecule through some currently unknown route, but let's just figure that we had this. And it took us a year to make this, and we had a kilogram of it made. And so we were all in on this route, but it kept giving us the dimethyl acetal. What might we do instead that might be selective? Two-step process. Yeah? What would that do?
You want the carboxylic acid to step down?
Yeah, how would we go from here to here? You're saying it. Just so SOCl2, what would that make?
It makes
Acid chloride, right?
Sorry, and
That's fine.
Gilman.
Well, no, not a Gilman. MEOH. Yeah, because it's a methyl ester. Methyl ester. Yeah, you're thinking over there. But yeah, so you could make the acid chloride, which would be selective, right? And then you can just add methanol to it. Or diazomethane, perfect. That's even simpler. Perfect. Diazomethane would be another option. So again, there are other options, right? So sometimes this is sort of when you start revisiting it. Now I think that this sort of idea of a Gilman is sort of fine. I often urge people to not use Gilmans when they are doing problems at home, because the Gilman reagent can oftentimes bring it out in an exam, no problem, right? But I think oftentimes the Gilman, you can sort of use it all the time, right? Like, and then you might not develop some of the other reactions. So let's think about a route that doesn't require a Gilman. And I really like this approach up here. But I also like the fact that, again, because we could probably make this without the Gilman, I'm sure, as well. But is there a way, say for example on this molecule here, right, we have CO2, right? And so CO2 if we wanted to say, for example, add CO2, right, we cannot do this, right? But do we know no, hold on, wait. Don't start shouting at stuff. Do we know a nucleophilic substitute for CO2 that's the same oxidation state? Cyano group. Now, actually, I don't know if the cyano would add 1,4 or 1,2, I gotta be honest, but I think it's fine to assume that you could, right? So, and I don't know, I actually don't know if that would work or not, but I think it's reasonable. Then a cyano, you could at least, I'm sure that you could probably work out conditions. I see somebody looking up, can cyanos add 1,4? So, and this is the reason why I think you probably could, is that, remember, what are the differences between cyanos, right? I mean, I could make an argument either way, I just don't know. But I think it's reasonable to propose a synthesis, you know, where a cyano could add either way, because I'm sure that people have worked out conditions to add at 1,4. But certainly we know that the LUMO in an alpha-beta unsaturated group is here, right? But the electrostatic one would be here. And we've seen Grignards and alkylithiums add here. We've seen cuprates and enolates add here. The Gilman, this sort of cyano is kind of weird because that negative charge is probably fairly concentrated on this carbon in much the same way, but it's also fairly stabilized. So I don't know, but it could be. It could be. I'd be curious. I certainly, if I'm sitting here scratching my head, if you probably showed either on a synthesis problem, I would be okay with it because I think it would show. That's where we come back to the mechanistic foresight. Like, you know, I bet you if we looked it up, people have worked out conditions for both. You know, so yeah.
Wouldn't you just add water across the double bond and then make a Grignard and have the CO2? Because it's one thing we'll probably add out of my car is the other time.
Well, so are you with a cuprate or something else like that? I mean, oxymicals certainly are reversible, right? But again, I would probably, in a synthesis problem, I would probably be okay with it, right? What's being said is if you added OH minus.
No, always.
Oh.
An H3O1. And then the.
Yeah. You know, for a synthesis problem, I would probably be all right with it. I don't know if it would work or not. In part because you have the reversible reaction and you would be relying upon that. But again, we've discussed in the past that if you're in an aqueous solution, you can drive it if there's enough water. So in principle, I'm sure that you could possibly do it. In fact, you may go all the way back, right? If you're going to go that approach, right, the problem might be that if you took this and treated it with acid and water, right, and this is still under acidic conditions, what might happen? Yeah, you may do a retro alcohol. So again, it's fine. I think that's the type of healthy question that I like you guys asking, right? I don't really like necessarily you guys memorizing, but it's a good healthy question. Mechanistically, you can draw it, and so if you can draw it, then somebody's probably figured out a way to get it to work, and if they haven't, then you got to figure out, well, why doesn't it work, and how might you get it to work? And this is how a lot of projects from synthetic chemists sort of are developed. But yeah, so I think again, you know, cyanide, you know, would be another option. So again, we've got some options here. But hopefully the point of this was, again, think backwards. Sometimes it can be really helpful. And if you're good at thinking backwards, perfect example, well, maybe I won't go to it because some people have had the quiz already, but there was a quiz question recently that I think if you just thought one step backwards, it simplified the question dramatically and made it significantly easier. So, anyway, think retrosynthetically. So with that, you know, I don't have anything to tell you in 2 minutes. If you have questions, come on up and I'll answer them.